Our next lesson is going to be on Gas Laws 3, and in this lesson we're going to look at three things. We're going to look at partial pressure, go over this a little bit more. We talked about this at the beginning of the unit. We'll talk about using partial pressures, how to find the partial pressures of gases, and we'll talk about gases collected over water is the term used, and about vapor pressure, about water vapor pressure. So first talk about partial pressure. Earlier on we talked about that gas pressures, that the reason why gases put pressures on the sides of their container are because of the fact that the molecules of gas are moving around, and when they move around they impact the surface, the surface of their container, so they hit that surface, and as those molecules basically run into the surface, they put a force on the container. And so by putting that force, that's where the pressure comes from. And so, start off with, that's just sort of our first statement here. Gas pressures are caused by the impact of gas molecules on the surface of its container. But what if we have a mixture of gases? For example, the air. The air is mostly oxygen and nitrogen, but there are some other things that are involved too, so carbon dioxide and water vapor and some other trace gases. So we have a mixture of different types of molecules in this gas we call air. In mixtures of gases, each type of molecule exerts its own pressure. And so we can talk about the impact in air of the oxygen molecules against the wall of the surface. And so the oxygen molecules are going to put a pressure against the wall. And then the nitrogen molecules are going to run into the wall and put a pressure on that. And so each of these types of molecules that exerts its own pressure, this type of pressure is called the partial pressure. And so we could talk about in a container of air, the partial pressure due to oxygen or the partial pressure due to nitrogen, or so on and so forth. The way it ends up working, though, is that each of these different types of gas in a mixture of gases, each contributes its own pressure, and so the total pressure then is going to be simply the sum of the partial pressures. And so we sort of got that down at the bottom here, that the total pressure on a gas is equal to the sum of the partial pressures. So if I have gas 1, 2, and 3 here, plus some other various gases out here, that the partial pressure of the first gas plus the partial pressure of the second gas plus the partial pressure of the third gas plus the partial pressure of what other gases are remaining, if we add those pressures up, we're going to get the total pressure on the gas. And so that's basically how partial pressure works. And we discussed that a little bit sort of earlier on in the year. So let's take a look at how we might apply this. So suppose we have a mixture of nitrogen and oxygen gas. We're told that the partial pressure of the nitrogen is 606 torr, and we're told that the barometric pressure is 777 torr. So the question is, what is the partial pressure of the oxygen gas? And so, well, here's what we know. We know that the total pressure is simply equal to the sum of the partial pressures. In this case, we have a mixture of two different gases. We have oxygen and we have nitrogen. So we have a partial pressure of the oxygen and a partial pressure of the nitrogen. So do we know the total pressure? Yes. The barometric pressure, that is the pressure of the overall pressure of the gas, is 777 torr. So we have 777 torr is our total pressure, equals the partial pressure of the oxygen plus the partial pressure of the nitrogen. We don't have the partial pressure of the oxygen, that's what we're looking for, plus the partial pressure of the nitrogen, which we're told is 606, so plus 606 torr. And so if we want to find what the partial pressure of the oxygen is, we simply want to subtract off 606 off both sides. And so in doing that, we end up with a partial pressure of the oxygen should be equal to, what is that, 171, I believe? I'm doing it in my head, right? 171 torr. And so in this case right here, that's going to be our final answer. Significant figure-wise, this is rounded to the ones place, this is rounded to the ones place, and so our answer will be rounded to the ones place. And so 171 torr is the partial pressure of the oxygen. Just like we said, if you add up the partial pressures, you get the total pressure. Now, here's where we sort of move with this, and here's the reason why this is important. Let's suppose that we have a mixture of, once again, nitrogen and oxygen gas, and we want to find the number of moles of nitrogen that are in this container. To do that, we could apply the ideal gas law. But the problem is that with the ideal gas law, if we use the total pressure, we won't find the number of moles of just nitrogen. We'll find the number of moles of both nitrogen and oxygen. So if we want to find just the number of moles of nitrogen, we don't want to use the total pressure. We instead want to use the partial pressure of the nitrogen that's sort of up here. So the rule is basically this. When you're ever applying the ideal or the combined gas laws for individual gases in a mixture, so, if I have a mixture of nitrogen and oxygen, just the nitrogen or just the oxygen, then the partial pressure is used, not the total pressure in any calculation. So in a mixture, if you're looking for one thing, you always use the partial pressure. So let's see an example of how this might work. And so taking a look here, if I can get my computer to listen to me. All right, so in an 18-liter mixture of nitrogen and oxygen gas, the partial pressure of the nitrogen is 606 torr and the barometric pressure is 777 torr. If the temperature is 370 K, how many moles of oxygen are collected? And so well, let's start this off here. Is that first question you always want to ask is this gas changing? And it's not going from one type of gas to another. It's not changing its volume or its temperature or its pressure. So we're going to use the ideal gas law. So PV equals nRT. And so let's set this up. So the pressure. Total pressure, the barometric pressure, is 777 torr. The question, though, asks how many moles of oxygen are collected. And so the barometric pressure would be both oxygen and nitrogen. So we don't want to use the barometric pressure, the 777. We instead basically want to use the partial pressure of the oxygen. And so we found on the last one here that the partial pressure of the oxygen, we just take the 777 minus the 606. And so when we do that, we said we got 171. So that meant that the partial pressure of the oxygen gas is going to be 171 torr times the volume of the gas, which we're told is 18 liters, equals N, the number of moles. That's what we're looking for. How many moles? Times the R, which for the units we're using here, 62.36. And then our last one would be the temperature. The temperature is 370 K. It's already in Kelvin, so we don't have to round any. So 370 K right here. And so at this point, all we have to do is solve for N. And so divide both sides by 62.36 and what is the other one? 370 K. So 62.36 and 270 K, divide both sides by both of those. And so that cancels these guys up here. Working out the math on this, we end up getting, let's see, 171 times 18 divided by 62.36 and then divided by 370. And so in doing that, we get that N, in this case, the number of moles, is going to be equal to 0.13340 moles. Significant figure-wise, that the pressure has 3 significant figures, the volume has 2, the 62.36 is a constant, so it's infinite. The temperature, we said we always round to the ones place, and so this one's going to have 3. So our final answer is going to have 2 sig figs, and so our number of moles would be 0.13 moles of, in this case, oxygen gas. And so that's how you go about using the partial pressure in order to find the number of moles of one of the types of gases in a mixture. So that's sort of what we've got with that. So onward we go. Let's say we have a case like this. A reaction occurs in a sealed, flexible container of argon, which releases 0.35 moles of hydrogen. After the reaction, the container is brought to STP. What is the partial pressure of the argon? So in this case right here is that the container is brought to STP. So there is sort of a change in the gas, but we're not told anything about what the original conditions were. We don't know when the reaction happened, what the pressure, the temperature, the volume is. All we really know about what we've got here is that we had 0.35 moles of hydrogen. And so we're looking for the partial pressure of the argon. And so we know this, that the total pressure is equal to the partial pressures. In this case, there'd be a partial pressure of hydrogen plus the partial pressure of the argon. And so let's see what we know. We know the container is brought to STP. If it's brought to STP, that means the total pressure has to be 760 torr. And this would equal the partial pressure of the hydrogen, which it doesn't say what that is. That's hydrogen, plus the partial pressure of the argon, which is what we're looking for. So we're still sort of, we got one piece here, but we got to find what that partial pressure of the hydrogen is. And so we know the number of moles of hydrogen. And so to find the pressure of hydrogen, we're going to have to go ahead and set up our equation. Since we're not changing, as we said, or at least we don't know anything about what the previous was, the only one we can use then is going to be the ideal gas law. So we have PV equals nRT. And so the pressure, do we know the pressure of the hydrogen to start with? We really don't. And so that's just going to be our pressure here. What about the volume? Do we know that? We actually don't here. So let's take a look at what we got. Looks like then I forgot to put in what the volume of this container is. And so let's go ahead and say that a sealed flexible container of, let's say right here, that it's 2.2 liters. That'll make this so this is actually doable. We couldn't do the problem otherwise. And so we'll say, so the volume in here is 2.2 liters equals N, the number of moles. We know the number of moles of hydrogen. It's 0.35 times R, which is 62.36. And then times the temperature, which he said is brought to STP, and so that would be 273.15. If I can fit this in. Woo, it's close. Okay, and so now to solve for pressure, we're going to divide both sides by 2.2. And so getting out the calculator, we say that we've got 0.35 times 62.36 times 273.15, because it's STP, divided by the volume, 2.2. And so we end up getting, in this case, 2,709.89. And so the pressure is 2,709.89. And the unit here is going to be in torr, which gives us a little bit of a problem. So I think I made a mistake on that little volume that I added up there before. Instead of being 22, let's actually go ahead and let's change that. And I apologize for this. That's what I get for not working out this problem before I put it in here completely. So let's change that volume to 22 liters. And so instead of having 2.2 down here, we're going to change things to be 22. And I just deleted, like, wow, that's a lot of stuff there. Let's just go ahead and reset that right there. And I'm going to get rid of this guy down here. Let's work this out just a second right over here. So in this case, we have the pressure, which we don't know, times the volume, which in this case would be 22 liters. And so we got to divide both sides by 22. That should give us a better answer here. And so working out the pressure here, then let's go ahead and reset this guy. And so we say, let's see, 0.35 times 62.36 times 273.15. And then we take that and divide it by 22. And so I get 270.98 is what we get for the pressure. So 270.98 torr is what we get for the pressure. Now, because of the fact that what we used here is we used the number of moles of hydrogen in here. That's the number of moles that we used right there. It means that this wasn't the total number of moles, not of hydrogen and argon. Since this is only moles of hydrogen, that means this will only be the partial pressure of the hydrogen. And so this is our partial hydrogen pressure. So once we've got that, we can go back over here again, and we can take a look at our original total pressure calculation. So 760 equals the partial pressure of the hydrogen, which we found to be 270.98 torr. 270.98 torr plus the partial pressure of the argon right there. And so to solve this, we're just going to subtract off our 270.98 from both sides. And so we end up getting a partial pressure of the argon, in this case, would be 760 minus 270 I can't get this to work right. Minus 270.989. And so we get 489.011. 49.011 torr is the partial pressure of the argon. Significant figure-wise is taking a look back over to what we did on the right side is the 22 liters has 2 sig figs, the 0.35 has 2 sig figs, 62.36 is infinite, and so is the so is our 273.15 because that's at STP. So that means that our 270.98 9 should have 2 sig figs, so it should be rounded to the 2 and the 7 are the significant figures here. And so in this case, so this one right here on the other side, then the 270 should be rounded to the 10 spot. The 760 is from STP, so it's infinite. That means our final answer should be rounded to the tens place. And so then that would mean these two guys are significant. So our actual final partial pressure of the argon would be 490 torr. And that's going to be our final answer. So 490 torr would be the partial pressure of the argon in the container. So let's go onward then. So the place where this partial pressure issue is going to be most used is going to be whenever we're actually collecting gases as we would be in a lab. Because one of the problems is that if, let's say that you do an experiment, you react two things together, and it produces a gas. In most cases, most experiments we tend to do, there tends to be air around. And so, as a result, any gas we produce tends to be contaminated by the air, contaminated by the atmosphere that it's around. And so, as a result, to prevent atmospheric contamination of a gas that's in a reaction, oftentimes gases are collected what's called over water. And so, gases are collected sort of over water is the term that's used. And what that means is the reaction takes place underwater, where there is no air, and the bubbles that come off of that reaction of any gas that's produced collect at the top of the container. And so we have a water-filled container to start with. There's no air in it. There's no way for air to get into it or any other sort of atmospheric gas. We do the reaction underwater. The bubbles that form from that gas produced in the reaction come up to the top of the container and then are not contaminated by any air. Now, there are other gases, though. In this case, there's actually one other gas, and that's water vapor. So such gases are thus a mixture of the collected gas, the one that we actually created in our reaction, and water vapor. And so what that means is that if we find we have the total pressure of that gas that's in the top of our container, the one we've collected here, it's going to be a combination of the partial pressure of the gas plus the partial pressure of water vapor, H2O. And I don't know what's going on here. So that's what we've got here to start with. So what that means is if we're able to measure the pressure of a gas that we collect, in order to find the partial pressure of the gas we're interested in, that is, do any type of gas calculations, we have to subtract off our water vapor pressure that's right in there. And so in order to do that, we need to find a way of finding that water vapor pressure. Fortunately, we've already got one of these. You have a colored sheet, which is the vapor pressure chart for water. And so this right here is basically our water vapor pressure table. And so we must consult one of these to find the vapor pressure of the water in the mixture, and thus the gas's collected partial pressure. The collected gas's partial pressure. And so if you look at your vapor pressure chart, then it tells you that if we do a reaction, and let's say that the combination of the two gases, the total pressure, the barometric pressure, is 760 millimeters of mercury. And if we did the reaction at 40 degrees Celsius, then we look on our vapor pressure chart and we see that 40 degrees Celsius corresponds to a vapor pressure of 55.4. And so if we wanted to find the partial pressure of our collected gas, we take the total pressure, 760 torr, and subtract from that the 55.4, which is the partial pressure of the water vapor. Whatever's left there has to be the partial pressure of the gas we're interested in. So that's basically called collecting over water. And so if you ever see something that says that this gas was collected over water, it means in any gas law calculation you do, you have to subtract off the water vapor pressure. And so that's going to be your first step. And then once you've got that partial pressure of the gas, then you can use it in its calculation. If a gas is not collected over water, if it is a pure gas, there is no contamination, and there's no water vapor involved, we found some other way of collecting the gas, or it's a case where basically you collect the gas over water and then dry it out. That gas is called a dry gas. And so if it says that such and such is a dry gas, it means you don't have to worry about the water vapor pressure. You can just go ahead and use the total pressure as your partial pressure of the gas. And so over water means you have to subtract off the water vapor to find the partial pressure. A dry gas means you don't have to subtract off the water vapor because there is no water vapor involved. So an example on this. So a sample of oxygen gas is collected over water. Is measured to have a volume of 17.4 milliliters and a pressure of 745 torr when the temperature is 20 degrees Celsius. How many moles of oxygen were collected? And so to get this to work, we look at it and we say, all right, we're looking for moles of oxygen And moles, pretty much, well, this tells us right off the bat we're pretty much going to have to use the ideal gas law. So PV equals nRT. Other hint here is the fact this gas isn't changing. So we're looking for moles of oxygen. So that means we need the partial pressure of the oxygen. We have 745 torr. This is the total pressure. So what we have to do is we know the total pressure is going to be equal to the partial pressure of the gas, in this case the oxygen, plus the partial pressure of water vapor. We know it's water vapor because it tells us it's collected over water. So we have a mixture of oxygen gas and water vapor. The total pressure is 745 torr. The partial pressure of the gas is what we're looking for. And we're going to add this to the partial pressure of the water vapor. Well, how do we know what the partial pressure of the water vapor is? Well, in this case, we're told that the temperature is 22 degrees C. And so if the temperature is 22 degrees C, then we look at our vapor pressure chart. Actually, just for the purposes of doing this, once again, I'm going to make a little change to my problem. And so let's say instead of being 22 degrees C, let's say temperature is going to be 20 degrees C, just to make this a little bit easier here. And so the temperature is 20 degrees C. We look at our vapor pressure chart, and we see that at 20 degrees C, that the vapor pressure is 17.5 for oxygen. And so that means we'll go ahead and we'll say that the water vapor pressure is 17.5 torr. And so to find what our partial pressure of the oxygen gas is, we'd say the 745, the total pressure, minus the partial pressure, 17.5, and we get a partial pressure of the water vapor. Sorry, not partial pressure of the water vapor, partial pressure of the gas, the oxygen gas, is going to be 727.5 torr. So down here we say our pressure we're going to use is going to have to be 727.5 torr, because torr is the unit we want to use here, times the volume. Do we know the volume here? It's measured to have a volume of 17.4 milliliters. Now, the problem we run into here is if we are in milliliters, that to use the R as 62.36, we have to be in liters. And so we have to convert this from milliliters to liters. And so to do that, normally what we do is we go ahead and set up our table. And so we'd say 17.4 milliliters, set up the table here. We go from milliliters to liters. And what we know is that there are, in 1 milliliter is 0.01, I think that's right. Nope, 0.001 liters. And so we'd say 17.4 times 0.001 liters. We end up with, this case, a volume of 0.0174 liters. Okay, we got that there because that cancels off milliliters and leaves us only with liters. Equals the number of moles, which is what we're looking for, times R. Since we have torr and liters here, it'll be to 62.336 times the temperature, which is 20 degrees C now. And so we add that to 273.15, and so we end up getting 293.15 Kelvin, because it has to be in Kelvin for this. So to solve for N, we're going to divide both sides by 62.36 and 293.15. And we'll say the same thing. I'll draw an arrow over here. Same thing over here, so I have to rewrite it here. And so to do this, we'd say the partial pressure of the oxygen, 727.5, times the volume, 0.0174, divided by 62.36, and then divided by 293.15. And so in so doing, we find that the number of moles here is going to be, I get 6.9246 times 10 to the negative fourth moles. You might have gotten 0.0006294. It's the same thing. Significant figure-wise, let's take a look that our pressure, 727.5, we'll have to look back at our original values here. 745 has 3 right over here, so this guy has 3. The water vapor pressure has 3. We're adding these, so we got to look at the places. 745 is rounded to the ones place. 17.5 is rounded to the tenths place, so our final answer here should be rounded to the ones place. So this will have 3 significant figures, and so this should have 3. Our volume is 17.4, which just has 17.4, which just has 3 significant figures. Our 62.36 is exact. 293.15, we had a temperature that was rounded to the ones place, so this should be rounded to the ones place as well, so it has 3. And so that means our final answer should have 3 sig figs. And so our final answer here, the number of moles, is going to be 6.92 times 10 to the negative fourth moles of oxygen gas. And so that is how you go about figuring that out. All right, so that's how you do that. Our next guy here. Let's say that a gas is collected over water, is found to have a volume of 89 milliliters when the temperature is 18 degrees C and the barometric pressure is 99.8 kilopascals. The gas is dried and brought to standard conditions. What is the new volume of the gas? So we're looking for the volume. We have to say, is this collected over water? And it says, yeah, collected over water. So we are going to have to, since we're looking for oxygen, or actually, I guess, we're looking for a gas. We're looking for the volume of that gas. We're going to have to worry about water vapor here. We have to now ask, is this gas changing? And it says that it starts off with a volume of 18 degrees C and a pressure of 99.8, and it's brought to standard conditions. And so this gas is changing, so we're going to use the combined gas law. So setting this up, we have, P1 V1 over T1 equals P2 V2 over T2. Now, P1, let's start with the original pressure here. So in the case of the original pressure, we know the barometric pressure is 99.8. But that's the pressure of both gases. We are drying this gas, which means we're taking the the water vapor molecules out. So we can't use the total pressure because the total pressure is both types of things, both the collected gas and the water vapor. We're going to have to find for P1 what the partial pressure of our collected gas is. Now, we know that we have 99.8 kilopascals is our original pressure, and that's going to be equal to the sum of the two pressures, that is the partial pressure of the gas plus the partial pressure of the water vapor. Well, we're told it's at 18 degrees C, and so once again, I'm going to make a slight modification to this just based on the table that you've got here. Instead of 18 degrees C, let's say we're at 15 degrees C. So with 15 degrees C, to find what the partial pressure is, we look at our vapor pressure chart, and at 15 degrees C, it tells us the vapor pressure in kPa is 1.70. And so that means that we got 1.70 is our partial pressure of water vapor. And so to find the partial pressure of the gas, we simply have to subtract that 1.70 off the 99.8. And so 99.8 minus 1.70, we end up with 98.1 kPa. Okay? And so to set this up is that we have, this is our combined gas law, and so since it's combined gas law, then it means we don't have to worry about what the pressure units are as long as they're the same on both sides. And so we're okay with using this 98.1 for this one. And so we say the partial pressure is 98.1 kPa is the original pressure times the original volume. The original volume is 89 milliliters. Once again, because of the fact that this is a combined gas law problem, we can leave it in milliliters. We don't have any trouble with that. The original temperature, we say 15 degrees, and so we say 15 degrees plus 273.15 because the temperature does have to be in Kelvin, so 15 degrees plus 273.15. Wow, I can't type today, 273.15. So we get 288.15 Kelvin equals, on the other side, the second pressure. And so it's brought to standard conditions. And so the atmospheric pressure at STP in kilopascals, which it has to be because the other one's in kPa, is 101.3 kPa. Times the volume afterwards, which we don't know. That's what we're looking for. That's V2. It will have to be in milliliters because our other guy's in milliliters, but we don't know what it is right now. Then the temperature, standard conditions, is 273.15. All right, Kelvin. And so our units match up. We got kPa on both sides. We have Kelvin on both sides, and the volume will come out in milliliters. And so to get this to work, we're going to go ahead and solve for V2 by cross-multiplying. We take the 273.15, multiply it up to the top here, the 101.3 kPa, bring it down to the bottom to divide by. And so when we do that, to find our total volume, V2, we'd say 98.1, which is the volume of the partial pressure of the gas, times 89 milliliters times 273.15 because we brought that up to the top, divided by 288.15 Kelvin, and then divided by 101.3 because we had to divide that off by cross multiplying. And so by doing this, we end up with a total volume, V2, of 81.7 milliliters. Significant figure-wise, let's take a look at what we've got. We started off, in this case, with original pressure was, let's see, where'd it go here? 99.8 kilopascals, so 3 significant figures. So 3 sig figs right up here, right into the ones place. The tenths place. We subtracted off our partial pressure to water vapor, which round to the hundredths place. That means our answer will have to be, so we have tenths and hundredths will be the ones least precise. There's the tenths place. That means our other guy, we round to the tenths place. So this has 3 significant figures. 89 milliliters has 2. 288.15. We added on 15 degrees up here, and so that's round to the ones place. So this will have to go to the ones place. So that has 3 significant figures. 101.3 is STP. That's exact because that's defined. 273.15, that's STP. That's exact and defined. So our smallest one is our 2 sig figs for the milliliters. And so that means our final volume here will be 82 milliliters. And so that's how you'd go about finding out, using the combined gas law, with a gas that has a partial pressure due to water vapor. And so that's sort of what we've got there.